But what matters is when we consider the function, when we consider the question of where the conversation is going. That motivates the concept of limit. I want to predict, when I say something like A, what you're going to say. If the prediction is that you're going to say something like L, why does this prediction make sense? It's because I can say something close to A that will prompt you to say something as close to L as possible. That counts as a prediction. So meaning that if our conversation, your emotion is predictable, I can generate prediction. And that is in fact the concept of limits. And I don't know if my predictions are right or wrong, but if it's validated in our conversation, that means continuity, because L is in fact, in this case, f of A. In this case, not only the emotion is predictable, it is also actually present in the conversation. So my flow of emotion will also lead to a flow of emotion on yours. And that is just how sequential continuity is defined. There are unpredictable emotions. For example, emotion suddenly jumps, and it's no longer possible for me to predict. Or your emotion oscillates so quickly that it's impossible for me to understand. And these are some things about this continuity. So several theorems about continuity, properties about continuity. What I want to emphasize is one of the three important theorems is called intermediate value theorem. So it basically shows, in our conversation, if you have your emotion reaches a point A, for example, and after a while, you reaches point B, then you must have reached everything in between. That's basically what the intermediate value theorem suggests. But how do we prove such things, right? The proof goes the following. If you need to reach some point in between, let us consider all the emotions that are lower than that point and all the emotions that are higher than that point. They both gotta approach somewhere. The lower one's gonna approach upward to some limit. The upper one's gonna approach lower to another limit. And these two limits must be the same and be actually defined by the function. Why? Because emotional changes are predictable. If they're not the same, you're gonna have a jump situation. If it's not recorded, it's not gonna be continuous anymore. So this is how we go about proving intermediate value theorem. I will talk about mean value theorem once we have like differentials, idea about differentiability. Uniform continuity just means I not only know how to predict your emotion, I know exactly how close I need to be to say something around A for you to say something close to my prediction. I know exactly how close. So I have perfect control over that conversation. This actually teaches a lesson as well, right? If we have conversation with somebody, we better be emotionally stable, because otherwise it will be discontinuous, and nobody will care about discontinuous things. Like basically in mathematics, right? So we want to make the conversation meaningful. We want to make sure we're emotionally stable. So the differentiability is defined as a rate of change, right? Emotional rate of change. So it's defined using limit, meaning that if a function is differentiable if we have a predictable emotional change. If we have a three-person conversation, I tell you something, you tell another person. What is the other person's emotional change rate with respect to my emotion? It is going to be his emotional change rate or her emotional change rate with respect to yours, multiplied by your emotional change rate with regard to mine. And that is exactly what chain rule is about. We can think of emotional changes as another function, as another conversation to the input, meaning that the differential is basically another function, another conversation. And in fact, the definition of differential is that it is the rate of change. It is the order of change. In fact, it only multiplies based on the input that I'm saying. So the differential should be something of a linear function. And that is, in a group-to-group conversation, the differential is a linear function. There is unpredictable emotional change. For example, the biasless function is nowhere differentiable because it just fluctuates too quickly. It's going downward, upward, downward, upward. Although it's predictable for emotions, but it's unpredictable for emotional change rate because it constantly shifts. Okay. We have several things about differentiability that follows intuitively with this as well. The thing I want to emphasize is mean value theorem. Meaning that if I only have 2 points in our conversation, you have reached point A, you have reached point B. you have an average change rate, right, from A to B. I want to know that you're definitely going to hit that change rate somewhere in between our conversation, in your conversation from A to B. Why is that true? Suppose you're always going below that average rate, right? Then you're never going to reach point B. Suppose you're always going above that average emotional change rate, then you're going to go beyond. You're going to get more excited at point B. In fact, trying to hit right at B, you have two choices. You either go always at the average rate, which we're done, or you kind of switch gears from lower than average to higher than average. But when you try to switch gears, in order for the emotional changes to be predictable, you gotta hit the average. You cannot just go abruptly. And in fact, that will make the emotional change rate unpredictable. And this is how we go about the proving like mean value theory. In fact, lower than average, higher than average is easier to prove mathematically using negative and positive. That is why Rollo theorem was developed first as a lemma to proving mean value theory. Obviously, if the emotional rate is predictable, the emotions are predictable as well, right? So that's why differentiable implies continuity. So we can then talk about what information is actually present in the conversation. In a linguistic perspective, trying to analyze the information present in conversations is hard. So what they do is they break down the conversation into smaller units. In each unit, they choose an anchor point, a word that contains an amount of information, and they try to estimate the amount of information for the whole conversation that way. And this is exactly the concept of partition. And in each partition intervals, we either analyze pessimistically, that gives lower integral. We analyze a little bit more optimistically, we give the upper integral. And in fact, you can think of this as a motivation for a measure theory as well. So the amount of information that our conversation gives from when I say A to when I say X is denoted f of X. So meaning that as long as our conversation is measurable in terms of information, then the information amount should be predicted, right? Intuitively makes sense. So this means that for an integrable function, the integral is actually continuous. And for a continuous function, the integral is differentiable, and that follows intuitively as well. We have fundamental theorem of calculus. And we can define things like log and exponential using the integral, right? But it also gives us an idea of how do we think about those kind of conversations. For example, log is defined something like this. Right? So it's defined as the integral 1 to x, 1 over ddt. So what kind of conversation is this? This is the conversation where I say something positive, you will definitely say something positive. You will never let me down. But when I get more excited, you get less excited. When I get less excited, you get more excited. Very weird conversation. But as I get more and more excited, the amount of information present in our conversation should increase less and less. And if we measure the information present in this kind of conversation as logarithm, it should rise slower than any conversation where your emotions increase as my emotions increase as well. So log will rise slower than any exponentials of x eventually. And that's what we can sort of analyze based on how the conversation looks. So there's times where information is not measurable in proper integrals and convergence of integrals. So imagine you're trying to found a startup and you're trying to get money from VC, for example. You're having multiple negotiations with them, and you're trying to understand globally where the series of conversation is actually going. For specific inputs, when you mention some certain things, you might have an idea of where the conversation is going. But in order to understand globally and generally, we need the concept of uniform convergence. And to make sure that the amount of information conveyed in each of the multiple conversations is actually a good reflection of what the final information is going to look like, what they're actually paying. We can only analyze this when the information is getting better and better, or worse and worse. We cannot analyze this when some part of the information is getting better, some part is getting worse. And this makes us confused, right? We don't know where the information is going to look like. So that's why we can only say about integral convergence when the integral converges monotone. And this follows from how the Lebesgue measure converges monotone as well. And in fact, this follows implicitly with the measure of information. So there's other things like equicontinuity and how we analyze different series of conversations. So we have seen some things where this theory works. But there are also certain things that this theory cannot take care of. First of all, in our natural language, there's no infinity. There's no infinitesimal version of anything. And this is something unique about math. And this is not taken care of in our daily communication. We don't know if I say something with like emotion infinity, what it's going to look like, what it's going to approach, where this conversation is going to go. We don't think it this way. And the second thing is, it is very difficult for me to incorporate topology, like open sets, closed sets. What does it mean for an alphabet to be open, first of all, right? It doesn't make any sense. It is hard for me to incorporate topology. But open and closed, compactness, connectedness, path connectedness is also a crucial part in real analysis. Right? We need that to establish other interesting properties. And there are certain things like product rules, for example. The proof is purely computational. You plug in the definition, and then you try to manipulate the formulas. And there's no intuition anyway behind computational proofs and computational results. And this is what the theory doesn't capture. But anyway, I hope at least this theory will not confuse you more. And it will provide you some more maybe intuition than we already have. And I think what I'm trying to do is trying to find a consistent way from the beginning to end that provides intuition for real analysis. And I know when I first enrolled in the first year calculus course here at U of T, it was, first day it was 400 students. And in the end, 80 of us went through. A lot of people got thrown off by the abstractness of these concepts. And they just decided not to do mathematics anymore, any further. And it is actually our responsibility to provide some intuition to help us adjust from high school level, computational level calculus to a little bit more abstract mathematical level. And so I don't know, to be honest, how the theory is going to go in the future. I'm merely presenting a possibility. And if you find it useful, you might start thinking about it. If you find it not useful, at least it doesn't confuse you that much. Maybe I will apply for a teaching assistant, like for first year calculus courses, and do some human experiment with this. But like in the coming U of T years, but I'm not sure how this is going to go. But anyway, that's my talk. I hope you enjoy it. Thank you. We do have time for questions. Yeah.
Any questions?
Yeah.
I'm interested in the history of this. Where did you like start the idea of, oh, maybe I should map back to natural language? How did it develop over time?
Yeah, like many times, like in science, right? The idea just comes all of a sudden, and I try to explain some of the deeper philosophical like aspects between natural language and mathematical language. But I didn't think of it that way when I first had this idea. I just think, well, it is interesting to analyze where the function is going, right? Is it increasing, is it decreasing? I probably was talking with my friend and things, and then this idea just came to me. But in order to make sure you guys understand this idea, I have to provide a little bit background. And I actually dig a little bit deeper and find out that there is several philosophical aspects that connects natural language and mathematical language. That was a surprise for me as well. I was hoping that this sort of intuition is just for me. It's probably not for everyone else, right? It's just some weird understanding that I have. But afterward, I discovered that it might be useful for other people, and that's why I decided to come here and do this talk.
Okay, thank you, Howard.